Good evening, everyone. How is everyone doing? Why a little bit stressed, Mr. Fisagi? I'm also well, thank you. How was last week's semester test? Then I'm glad. Then in tomorrow night's lecture, I will go through the memo for the test. Random biggest example, but tomorrow night I will go through the memo with you guys. And then I will also give you a bit of statistics on the test, on what the average it was, and those sort of things. Awesome. So for tonight's lecture, we are going to look at normal and active galaxies. Exam in a week's time. No, as far as I understand, the exam is only in July. I will tell you now. I'm just going to open a study guide on my side. I think I've got it in the study guide. Just see 20. Okay, got it. Study guide. Yes, just have to make sure. I will let you guys know, and I posted it on the group somewhere. But it's in July. So let me quickly check where I saved the date. I think you guys are right. There are three weeks left of lectures. Let me just check. I got it somewhere. The examination is the 21st of July. So for tonight's lecture, we're going to look at the family of galaxies, measuring the properties of galaxies, the evaluation of galaxies, active galactic nuclei and quasars, disk jets, eruptions, and galaxy evolution. So in this image, every object that we see is a different galaxy. But last week we now learned how galaxies formed, how our own galaxy operates. But what we learned we can transfer to other galaxies as well. And as we will learn in this lecture, we get a bunch of different galaxy classifications. So Milky Way galaxy is only one of the many billions of galaxies visible in the sky. This chapter will expand your horizon to discuss different kinds of galaxies, their complex histories, and violent eruptions. For this lecture, we are going to answer 5 important questions. Firstly, what are the different types of galaxies? Secondly, how do astronomers determine distances, sizes, luminosities, and masses of galaxies? Do other galaxies contain central supermassive black holes and dark matter, as does our galaxy? How do collisions and interactions affect the evolution of galaxies? How did supermassive black holes in a galaxy nuclei form, evolve, and affect their host galaxies? So we get 6 primary classifications of galaxies. We have our barred spiral galaxy, irregular galaxy, spiral galaxy that we are most familiar with, peculiar galaxy, elliptical galaxy, and lenticular galaxies. Science fiction hero effortlessly jump between the stars, but almost none travels between the galaxies. As you leave your home galaxy, the Milky Way behind, you will voyage out into the depths of the universe, out among the galaxies, into space so deep it is unexplored even in fiction. So for the sci-fi fans, you will always hear they're traveling around in a galaxy, exploring galaxies, but never other galaxies. And that's why it's also coming for the Star Wars saga as a long time ago in a galaxy far, far away. But now we're going to start to look at galaxies in whole and what happens to different galaxies and what happens in between galaxies. Yes, Mr. Levuyo.
Sorry, so this is a bit off topic. So, but out of curiosity, so even if we had to create like for example, so teleportation, so would it still be impossible for us to go explore other galaxies?
That is a interesting question. It all depends on how the teleportation system we are using is working. If it's such as Star Trek, um, where you use a transporter, then it is a couple of million kilometers. If we go to Stargate, then that can be across the entire galaxy, but all depends on what we are going to do or how teleportation works. So in theory, yes, that can be possible.
Thank you, sir.
So you all probably, yes, warp drive is maybe viable one day. So you all recognize this image of Chewbacca and Han Solo in a Millennium Falcon jumping to hyperspace. Astronomy books often include pictures of spiral galaxies. Like movie stars, spiral galaxies get a lot of attention because they are beautiful, but many galaxies are nearly featureless clouds of stars, and others are distorted muddles of gas and dust. You must begin by sorting out this jumble of galaxies. A century ago, photos of galaxies looked like spiral clouds of haze. Modern images of these relatively nearby galaxies reveal dramatically beautiful objects filled with stars plus clouds of gas and dust. So here we can see young blue stars illuminate in a spiral arms of this galaxy. Clouds of gas and dust in a small foreground galaxy visible in a silhouette against the background. Dusty disk of galaxy warped by interaction with another galaxy. New stars forming in dust clouds, and dust clouds glow red in this infrared image. Astronomers classify galaxies according to their shapes in photographs made at visual wavelengths using a system developed by Edwin Hubble in the 1920s. Such systems of classifications are fundamental technique in science. Many galaxies have no disk, no spiral arms, and almost no gas and dust. These elliptical galaxies, or class E galaxies, range from huge giants to small dwarfs. Secondly, disk-shaped galaxies usually have spiral arms and contain gas and dust. Some of these spiral galaxies, so class S, have a central region shaped like an elongated bar and are called barred spiral galaxies. So SB is for barred spiral. So learn in chapter 12 that a Milky Way galaxy is a barred spiral. A few disk galaxies contain relatively little gas and dust. These are called lenticular galaxies, so S0. Finally, notice the irregular galaxies, class I, which are generally shapeless and tend to be rich in gas and dust. So, which is important in this lecture is to remember elliptical galaxies, so E for elliptical, spiral galaxies, S for spiral, SB for barred spiral, and then S0 for lenticular, and I for irregular galaxies. It is surprisingly difficult to figure out what proportions of galaxies are elliptical, spiral, or irregular. In catalogs of galaxies, about 70% are spiral, but that is misleading because spiral galaxies contain hot luminous stars and clouds of ionized gas that make them easy to notice. Most ellipticals are fainter and harder to notice. Small galaxies such as dwarf ellipticals and dwarf irregulars are actually very common, but they are hard to detect. From careful statistical studies, astronomers estimate that ellipticals are actually more common than spirals, and that irregulars make up about 25% of all galaxies. So how many galaxies are there? Long exposure images of small areas in the sky are called deep field because they detect the most distant galaxies deep in space. So it's actually when you are speaking to cosmologists make use of these deep space images or deep images to study galaxies and to compare galaxies and to study galaxy evolution. So in this image we are looking at now, an apparently empty spot on the sky, only 1/13th the diameter of a full moon, contains more than 1,500 galaxies. In this extremely long time exposure known as the Hubble Deep Field North, only 4 stars are visible in this image. They are sharp points of light with diffraction spikes produced by the telescope. Evidently, the entire sky is similar field filled with galaxies. So why do you guys think we need an extremely long exposure to detect all these galaxies? So yes, it is possible that stars could exit a galaxy. It could be, yeah, there are. There are a few examples of those that we'll discuss in this chapter. But like we need an escape velocity to escape Earth, we need an escape velocity to escape our solar system. So the star that leaves its galaxy will also need an escape velocity. And yes, those objects are very far away and just very dim. So we need to capture a lot of light to detect those galaxies. So the mathematical term for a long exposure is integration time. So remember what you're doing. So when you do integration, you're basically calculating the area under a curve or a function. While in astronomy, when we say we are integrating longer, it's meaning we're trying to detect the area we're looking at for mathematical models, mathematical figures, and each figure will represent a galaxy or object we are observing. So when they speak about long exposure times, that comes from the photography terminology, but in astronomy, especially in radio astronomy, we call it integration times. So what are the properties of galaxies? What are the diameters, luminosities, and masses? Just as your study of stellar characteristics in Chapter 8, the first step in your study of galaxies is to find out how far away they are. Once you know a galaxy's distance, its size and luminosity are relatively easy to find. Later in the section, you will see that just as for stars, finding the masses of galaxies is more difficult, like we learned in previous chapters. If we know what a distance is to a star, then it's easy to find its size and luminosity. The same principle counts towards galaxies. So how do we find distance? The distance to galaxies are so large that it's not convenient to measure them in light years, parsecs, or even kiloparsecs. Instead, astronomers use the unit megaparsec. Are you guys still familiar and happy with the terminology of a parsec? Awesome. So just to put this in perspective, 1 megaparsec is equivalent to 3.3 million light years. So that is approximately 3 times 10 to the power 19 kilometers. So in this graph right here, we can plot the location of different galaxies that we've determined. So we have our y-coordinate, x-coordinate, and these are in megaparsecs. So how do we determine the distance to these galaxies? To find a distance to a galaxy, astronomers must search among its stars, nebula, and star clusters for familiar objects whose luminosity they know. Such objects are called distance indicators because they can be used to find a distance to a galaxy. Astronomers often refer to them as standard candles. If you can find a standard candle in a galaxy, you can judge its distance. Shaped variable stars are reliable distance indicators because their period is related to their luminosity. The period-luminosity relation has been calibrated so you can use the period of the star's variation to find its absolute magnitude. Then by comparing its absolute and apparent magnitudes, you can find its distance. So in this image, the vast majority of spiral galaxies are too distant for Earth-based telescopes to detect Shaped variable stars. The Hubble Space Telescope, however, can locate Shaped in some of these galaxies. For example, the bright spiral galaxy M100 form a series of images taken on different dates. Astronomers can locate Shapeds, determine a period of pulsation, and measure the average apparent brightness. They can then deduce the distance to the galaxy, so in this case for M100, it is 16 megaparsecs. I can't remember, but have I told you guys the classification of M, the Messier object classification? Okay, so let me describe both of them. So Hubble contributed a lot to astronomy, but one of the things he is most famous for is the Hubble constant. He figured out at a pace at which the universe is expanding. And the pace at which the universe is expanding is called the Hubble constant. So for those of you that's going to take the second year astronomy course, so the second year astronomy course is PHY 210. I'm going to type it in the chat. Last year I taught this module as well because the lecturer that usually taught this module were on sabbatical. So he's back. So currently I don't know if I'm teaching this module or yet, but if I'm not teaching, it's going to be taught by Dr. Satish Thorat, also a brilliant lecturer. And in this module, you are going to look at the same work as in SCI 154, but now you're going to look at more of the physics behind everything. And one of the questions that I set up for a practical for the module is to use Hubble's constant to determine the age of the galaxy. But so hopefully Dr. Thorat will use that question when you are taking this module. And then secondly, the M's. So we have different classifications for objects. M stands for Messier. So Messier was an astronomer, and he took his telescope, and every object he could see through his telescope, he designated M1 to, let me just check how many Messier objects there are. So there are currently 110 Messier objects. So it's from French astronomer Charles Messier. And he have done this work in 1774. So he has classified and categorized 110 objects from M1 to M110. But each year for the astrophotographers, there are a competition going around to see who can, every year, who is the first person that can photograph all Messier objects in one observation session. So you think, that's easy, but that's actually not easy because you need to get your timing in the year right that all 110 Messier objects will be visible. And then you need to have your equipment set up because some Messier objects you will see just before sunset, and some you will see just after sunrise. So that means while the sun is setting, you need to photograph, for example, Mercury is one of the Messier objects. Take a photo of it, then move on to the next object. And if you struggle with one object, that means you might miss it, and that will screw up your entire observation for the entire night. But that is called the Messier Challenge that happens each year. So do you guys recognize this telescope? Yes, our wonderful Hubble Space Telescope. And you know what a replacement telescope as Hubble is going to be. Yes, the James Webb Telescope. So the James Webb Telescope went way over budget and way over time. Its original launch date would have been 2012, but usually due to technical problems, funding problems, it was kept pushed back. So right now, if we are lucky and I keep the schedule, James Webb will be launched next year. Even with the Hubble Space Telescope, Shepherds are not visible in galaxies much beyond 30 megaparsecs. So astronomers search for less common but bright distance indicators and calibrate them using nearby galaxies that contain both indicators. For example, by studying nearby galaxies with distances known from Shepades, astronomers have found that the brightest globular clusters have absolute visual magnitudes of about -10. If you found globular clusters in the more distant galaxies, you could assume that the brightest of the globular clusters have an absolute magnitude of -10 and use that information to calculate the distance. Astronomers can calibrate type 1a supernova, those produced by the collapse of a white dwarf, because the white dwarf always collapses at the same mass limit. So the explosion reached approximately the same maximum luminosity. When type 1a supernovae occur in galaxies with distances that are known from Shepades variables and other distance indicators, astronomers can find the absolute magnitude of the supernovae at peak brightness. So we're going to look at the next figure. So when astronomers see a type 1a supernova in more distant galaxies, they observe the apparent magnitude of supernovae at maximum and compare that with the known absolute magnitude the supernova reach at maximum to find the distance to the galaxy. So in this image, we can see while dinosaurs roamed Earth, a white dwarf in the galaxy NGC 1309 collapsed and exploded in a type 1a supernova, and the light from that explosion reached Earth in 2002. The astronomers found Shepard variable stars in the galaxy, so they can determine that is 120 million light years away. And that allowed them to find the absolute magnitude of the supernova at its brightest. The supernova had faded from view 3 years later, even though the second image was made using Hubble Space Telescope. By combining observations of many supernovae, astronomers have been able to calibrate type 1 supernovae as distance indicators. So notice how astronomers use calibration to build a distance scale reaching from the nearest galaxies to the most distant visible galaxies. Often astronomers refer to this as the distance pyramid or distance ladder, because each step depends on the steps below it. The most dependable step is the Shepard variable stars, but notice that Shepard distance indicators depend on astronomers' understanding of stellar luminosities and of the stars in the HR diagram, and that rests on an even lower step in a ladder, measurements of the parallax of stars. Stellar parallaxes in turn depend on measuring the size of Earth's orbit around the Sun, which finally rests on the bottom step, measuring the size of Earth itself. The distance ladder ultimately connects the size of Earth to the most distant galaxies in the universe. The most distant visible galaxies are over 3,000 megaparsecs, so 10 billion light years away. And at such distances, you see an effect akin to time travel. When you look at a galaxy that is millions of light years away, you do not see it as it is now, but as it was millions of years ago, when its light began the journey towards Earth. When you look at a distant galaxy, you look back into the past by an amount called the look-back time, a time in years equal to the distance in light years the light from the galaxy traveled to Earth. So when we look at an object that is 7 billion light years away, the look-back time is 7 billion years. An object that is 14 billion light years away, it's 14 billion years. What do you mean? Why is the event horizon then 48 billion light years? What do you mean a certain distance to look back time? There's no distance, it's even around us. So yes, the cosmic horizon is 14 billion years, but we will get to that later in this chapter. But even if you look at someone, so for example, a good example at this is, if you are at a sports stadium, and for example, you're looking at the 400-meter dash, and you have the referee with the gun in one hand, and when he shoots the gun, it's a signal for the race to start. So if you are on the other end of that 400-meter dash, you will see the smoke from the gun first before you hear the gun. So that means you have a look back time of a couple of nanoseconds. So the further away you are, that larger that look back time is happening. So for example, if we look at a sun, it takes 8 minutes for sunlight to reach Earth. So say for example, the sun went blank, then it will take us 8 minutes to realize before something's happened to the sun. So another example we can use is the look back time to the moon. For the sunlight will take, say, roughly 8 minutes to hit the moon, but then it needs to be reflected from the moon to the Earth. And for the light to be reflected from the moon's surface to Earth takes 1.3 seconds. So that means our look back time is 1.3 seconds. So another good example is when Earth is on its closest approach to Mars. It takes light, or even not the right electromagnetic radiation, and light travels at the same speed. It would take 182 seconds to reach Mars, or 3.03 minutes. So that means when Mars is on its closest approach, it would take communication 3 minutes to get there, 3 minutes to get back. So for example, closest approach, if Mars will completely disappear, we will only notice it 3 minutes later. And for example, if we take Jupiter, that's roughly 43 minutes. Yes, exactly. Depending on where they are. If there's another civilization that's roughly 56 million light years away from us, and they would be observing Earth, then yes, they will still be seeing dinosaurs. So to prove this look back time is actually quite easy. So 1.3 seconds to the moon. Sun is 8 minutes. The nearest star to us, Alpha Centauri, is 4 light years away. So we are seeing how Alpha Centauri is 4 years ago. So the Andromeda galaxy that's the closest to Earth is 2 million light years away, so 2 million years. But these distances, even 2 years, is only a small fraction in our cosmic timescale. Now we start to get to the interesting stuff, Hubble's law. Although astronomers must work carefully to measure the distance to a galaxy, they often estimate such distances using a simple relationship that was first noticed at about the same time astronomers were beginning to understand the nature of galaxies. Early in the 20th century, astronomers were able to record the spectra of brighter galaxies. And most had redshifts as if they were receding. The faintest galaxies had the largest redshifts. In the 1920s, astronomers Edwin Hubble and Milton Emerson were able to measure distances to a number of galaxies using Shepard variable stars. And in 1929, they published a graph that plotted the apparent velocity of recession versus distance for their galaxies. So here we can see Edwin Hubble and Milton Amundsen's first diagram of the apparent velocities of recession and distances of galaxies. Did not probe very deeply into space, and the horizontal axis was later recalibrated. These data did show, however, that the galaxies are receding from one another. The simple relation between apparent velocity of recession and distance is known as the Hubble law, and the slope of the line is called the Hubble constant. The Hubble law has important implications. It is commonly interpreted to show that the universe is expanding. The distance to a galaxy can be found by dividing its apparent velocity of recession by the Hubble constant. This makes it relatively easy to estimate the distance to galaxies because a large telescope can record a spectrum of a galaxy and determine its apparent velocity of recession, even when it is too distant to have visible distance indicators. Edwin Hubble's original measurements of h were too large because of calibration errors in his distance measurements. The most precise modern measurements of h yielded to a value of 70 kilometers per second per megaparsec, with an uncertainty of just a few percent. So once you find the distance to a galaxy from distance indicators or the Hubble law, you can calculate its diameter and its luminosity. With a good telescope and the right equipment, you could easily photograph a galaxy and measure its angular diameter in arc seconds. If you knew the distance, you can use the small angular formula like we did in reasoning of numbers 3.1 to find its linear diameter. If you also measure the apparent magnitude of a galaxy, you could use the distance to find its absolute magnitude. So reasoning of numbers 8.2, and from that, its luminosity. The results of such observations show that galaxies differ dramatically in size and luminosity. Irregular galaxies tend to be small, 5 to 25% the size of our galaxy, and of low luminosity. Although they are common, they are easy to overlook. Our Milky Way galaxy is large and luminous compared with most spiral galaxies, though astronomers know of a few spiral galaxies that are even larger and more luminous. So yes, if you have the distance, you can use the small angular formula to find the luminosity. We've done that in reasoning 3.1 and in reasoning 8.2. The largest is nearly 5 times bigger and in diameter and about 10 times more luminous than the Milky Way. Elliptical galaxies cover a wide range of diameters and luminosities. The largest, called giant ellipticals, are 10 times diameter of our Milky Way, but many elliptical galaxies are very small dwarf ellipticals, only 1% diameter of our galaxy. Of the 3 basic parameters that describe a galaxy, you have found 2, diameter and luminosity. The third, as was the case for stars, is the more difficult to measure. So here we can see a reasoning of numbers, good example for the exam. The apparent velocity of recession for a galaxy, VR, in kilometers per second is equal to Hubble's constant h multiplied times the distance to the galaxy d in megaparsecs. So then we get this straightforward equation. Astronomers use this as a way to estimate the distance from a galaxy's apparent velocity of recession. So, example, if a galaxy has a radial velocity of 700 kilometers per second and Hubble constant is 70 kilometers per second per megaparsec, so remember this is a constant that will remain the same, then the distance to the galaxy equals the velocity divided by the Hubble constant. So we just manipulate this formula and we get a distance of 10 megaparsecs. So now we need to find the mass of the galaxy, and that is the most difficult part to do. Although the mass of a galaxy is difficult to determine, it is an important quantity. It tells you how much matter the galaxy contains, which in turn provides clues to the galaxy's origin and evolution. Although there are a few ways to estimate the mass of a galaxy, the most direct measurement of Kepler's third law of planetary motion. In Chapter 8, Section 5, we use that law to find the masses of binary stars. If astronomers can measure the radius of a galaxy and the velocity with which it rotates, they can easily find the orbital periods of the stars as they orbit a galaxy. Then they can use Newton's version of Kepler's third law to calculate the mass of the galaxy. The most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called the rotation curve of a galaxy. So here we can see a rotation curve. So in image A, in the upper panel's artwork representation, an astronomer has placed the image of the galaxy over a narrow slit so that light from a galaxy can enter the spectrograph and produce a spectrum. A very short segment of the spectrum shows an emission line redshifted on the receding side of the rotating galaxy and blue shifted on the approaching side. Converting those Doppler shifts into velocities relative to the galaxy's center, the astronomer can plot the galaxy's rotation curve. So that's on the right. Then it's over here. So in image B, real data are shown in the lower panel of galaxy NGC 2998. Is shown in the spectrograph slit, and a segment of the spectrum includes free emission lines. So you can see the free emission lines, and here we can see the rotation curve. The most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called the rotation curve of the galaxy. Using such a graph to find the mass of the galaxy is called rotation curve method. It is the most accurate way to find the mass, but it works only for the nearer galaxies whose rotation curve can be observed. More distant galaxies appear so small astronomers cannot measure the radial velocity at different points across the galaxy. Measuring the masses of galaxies reveal two things. Firstly, the range of masses is wide from 1 million times smaller than the Milky Way galaxy to 50 times larger. And second, galaxies contain dark matter spread through extended galactic coronae, just as does our Milky Way galaxy. One last region remains to be explored. What lies in the center of galaxies? Our Milky Way galaxy contains a 4 million solar mass black hole at its center. But the question is, do all galaxies contain similar objects? And what do you guys think? So say yes, possible. Okay, so you guys think so. So supermassive black holes in galaxies. So question, does the angular velocity of galaxy depend on the angular velocity of its black hole? No. Remember in a previous chapter we learned that certain parts of the galaxy rotates faster or slower than other parts depending on if it's a spiral galaxy on the arms and on the halo clusters. Rotation curve shows the motions of the outer parts of a galaxy, but it's also possible to detect the Doppler shifts of stars orbiting very close to the centers. Although these motions are not usually shown on rotation curves, they reveal something astonishing. Measurements showed that the stars near the centers of most galaxies are orbiting very rapidly. To hold stars in such small short period orbits, the centers of galaxies must contain millions or even billions of solar masses in a very small region. The evidence shows that the nuclei of many galaxies contain supermassive black holes. The Milky Way contains a supermassive black hole at the center, and evidently that is typical of galaxies. So yes, Mr. Visakhi is exactly the ice skating example. So why are galaxies circular or elliptical? That is due to the spiral arms of galaxies. Now the galaxies are formed, and we are going to discuss that next coming up. So this is our wonderful image of the black hole, and this is the black hole inside a typical galaxy. Such a supermassive black hole cannot be the remains of a dead star. That would amount to only a few solar masses. Rather, a supermassive black hole either formed as the galaxy formed, or accumulated mass over billions of years as matter sank into the center of the galaxy. Measurements show that the mass of a supermassive black hole is related to the mass of the central bulge. A galaxy with a large central bulge has a supermassive black hole whose mass is greater than a black hole in a galaxy with a smaller central bulge. Rare galaxies lacking central bulges usually also lack supermassive black holes. This suggests that the supermassive black holes formed long ago as the galaxies formed. Of course, matter has continued to drain into the black holes, but they do not appear to have grown dramatically since they formed. So how big does a supermassive black hole play in its respective galaxy? It plays a big role. The only way we can get a large galaxy is by having a supermassive black hole that keeps the matter together. So remember, you can think about it as our own solar system. All of our planets orbit the sun, and most of the solar system's mass is encapsulated by the sun. So the sun provides a gravitational pull to keep the planets in a stable orbit. So in a large galaxy, we need something to keep the stars in stable orbits around its center, and that something is a supermassive black hole. A billion solar mass black holes sounds like a lot of mass, but note that it's roughly 1% of the mass of the galaxy. The 4 million solar mass black hole at the center of the Milky Way galaxy contains only 1,000th of 1% of the mass of the galaxy. So where does this go? Given the size and luminosity of a galaxy, astronomers can make a rough guess as to the amount of matter it should contain. They know how much light stars produce, and they know about how much matter there is between the stars. So it's quite possible to estimate the mass of a galaxy from its luminosity. But the measured mass of a galaxy is generally 10 times larger than estimated from what is visible. This must mean that nearly all galaxies contain dark matter. X-ray observations reveal more evidence of dark matter. X-ray images of galaxy clusters show that many of them are filled with very hot, low-density gas. The amount of gas present is much too small to account for the dark matter. Rather, the gas is important because it is very hot and its rapidly moving atoms are not leaked away. Can planets form around? Yes, they can form around them as well. Evidently, the gas is held in the cluster by a strong gravitational field. To have a high enough escape velocity to hold the hot gas, the cluster must contain much more matter than what astronomers can observe directly. The detectable galaxies and the Coma cluster, for instance, amount to only a small fraction of the total mass of the cluster. So in image A, we can see the Coma cluster galaxies contain at least 1,000 galaxies and is especially rich in E and SO galaxies. Two giant galaxies lie near its center. Only the central area of the cluster is shown in this image. If the cluster were visible to the unaided eye, it would span 8 times the diameter of the full moon. Then in image B, In false colors, this X-ray image of the coma cluster shows it is filled and surrounded by hot gas. Note that the two brightest galaxies are individually visible in the X-ray image. Another way to detect dark matter goes back to 1916, when Albert Einstein described gravity as curvature of spacetime. The presence of mass actually distorts spacetime, and that is what you feel as gravity. He predicted that a light beam traveling through a gravitational field will be deflected by the curvature of spacetime, much as a golf ball is deflected as it rolls over a curved putting green, and that this would result in twice the deflection prediction by Newton's theory of gravitation. That effect has been observed and is a strong confirmation that Einstein's theories are correct. Gravitational lensing occurs when light from a distant object passes a nearby massive object and is deflected by the gravitational field. The gravitational field of the nearby object is actually a region of curved spacetime that acts as a lens and deflects the passing light. Astronomers can use gravitational lensing to detect dark matter when light from very distant galaxies passes through a cluster of relatively nearby galaxies on its way to Earth and is deflected by the strong curvature. The distortion can produce multiple images of the distant galaxies and distort them into arcs. The amount of distortion depends on the mass of the cluster of galaxies. So what this actually is? Here we have a gravitational lens. So here is a galaxy that's far away. So right now we have a quasar in between. We will discuss quasars in this image. So we can't see through the quasar because it has a giant gravitational pull. It actually bends light around it. So when we focus our telescope to this position, then we all of a sudden see a galaxy. So then we might think, okay, so the galaxy must be here somewhere because we see it over here. So it must be here somewhere, or it must be here somewhere. But in fact, it is being curved by gravitational lensing, and its true location is actually over here. Observations of gravitational lensing made with very large telescopes reveal that clusters of galaxies contain far more matter than what can be seen. That is, they contain large amounts of dark matter. This confirmation of existence of dark matter is independent of Newton's laws and gives astronomers great confidence that dark matter is real. Theorists conclude that dark matter must be made up of some as yet undiscovered subatomic particles that do not interact with normal matter, with each other, or with light. Dark matter is detectable only through its gravitational field. So this is just an artist's representation of what dark matter actually might look like in a galaxy. Dark matter is not an insignificant issue. Observations of galaxies and clusters of galaxies show that nearly 90% of the matter in the universe is dark matter. The universe you see, the kind of matter you and the stars are made of, has been compared to the foam of an invisible ocean. Dark matter remains one of the fundamental unresolved problems of modern astronomy. Question: so if most of the universe mostly contains dark matter, shouldn't light seemingly out of the blue lens even when there's nothing very on its path? So that's what's difficult. So it doesn't have any effect on normal light or electromagnetic radiation. The only way we can see effect of it is in gravitational fields. So in this image, we can see how gravitational lensing works. Here's Earth, here's a lensing cluster. So here is where the galaxy is. So we can draw an arc over here and an arc over here. So this is where we see the galaxy. We can actually see two images of the galaxy, but it's actually sitting right over here. So now we are getting to our classification. So now we know what the galaxies are, but how do they evolve? How are they forming? So every galaxy starts as a E0, then become a E3, so elliptical, elliptical, elliptical 6. Then from there on, it can become an S0 all the way to an SC, and then it dies off as irregular. So here is a barred spiral, and it goes on and it ends in an irregular galaxy. Yes, Mr. Lavuyo.
So how exactly do we know this thing? So because like, have we ever observed dead galaxies?
The galaxies, yes, we have.
A dead
So
galaxy.
all these stages of galaxies have been observed. So our irregular galaxies will be the oldest galaxies we can observe.
So these
But
galaxies, sorry, so these galaxies still give off light.
yes, they still give off light, there's still stars being formed in them, but they are not as active as young galaxies.
So the classification of a galaxy would be, I mean, like, so an active galaxy would be considered one that is always producing a lot of stars.
Yes, that forms part of the definition, but we will handle the definition in a couple of slides.
Thank you, sir.
Awesome. Considering the origin of our own Milky Way galaxy, presumably other galaxies formed similarly. But what did some galaxies become spiral, some elliptical, and some irregular? An important clue that the mystery lies in the clustering of galaxies. So here we can see our overview of how the universe started. It started from the Big Bang to where we are now. Single isolated galaxies are rare. Instead, most galaxies occur in clusters containing a few to a few thousand galaxies in volumes 1 to 10 megaparsecs across. Our Milky Way galaxy is a member of a small cluster, and surveys have catalogued thousands of other clusters. For purposes of this study, you can sort clusters of galaxies into rich clusters and poor clusters. Rich clusters contain 1,000 or more galaxies, mostly ellipticals, scattered through a volume of roughly 3 megaparsecs in diameter. Such a cluster is nearly always condensed. That is, the galaxies are more crowded near the cluster center. At the centers, such clusters often contain one or more giant elliptical galaxies. The Virgo cluster is an example of a rich cluster. It contains more than 1,500 galaxies and is 16.5 megaparsecs from our own galaxy. The Virgo cluster, like most rich clusters, is centrally condensed and it contains the giant elliptical galaxy M87 at its center. So this is what it will look like. So this is not true colors. This is just to show the distances of different clusters in the Virgo galaxy cluster. Poor clusters contain fewer than 1,000 and often only a few galaxies spread through a region that can be large as a rich cluster. That means that the galaxies are more widely separated. Our Milky Way galaxy is a member of a poor cluster known by the unimaginative name, the local group. So in this image here, we can see spiral, elliptical, and irregular galaxies, and this is our local group cluster. So the local group, our galaxy is located at the center of this diagram. The vertical lines giving distances from the plane of the Milky Way, are solid above the plane and dashed below. Then in image B, the Sagittarius dwarf galaxy lies on the other side of our galaxy. If you could see it in the sky, it would be 17 times larger than the moon. Then in image C, as shown as artist rendering of a mathematical model, the Canis Major dwarf galaxy has orbited around the Milky Way galaxy a number of times, and tides have ripped stars and gas away from streamers. The total number of galaxies in the local group is uncertain, but it probably contains about 40 galaxies scattered irregularly through a volume of roughly 1 megaparsec in diameter. Of the brighter galaxies, 15 are elliptical, 4 are spiral, and 13 are irregular. The total number of galaxies in the local group is uncertain because some galaxies lie in the plane of the Milky Way galaxy and are difficult to detect. For example, a small galaxy known as the Sagittarius dwarf has been found on the far side of our own galaxy, where it is almost totally hidden behind the star clouds of Sagittarius. Even closer to the Milky Way galaxy is the Canis Major dwarf galaxy. This galaxy was found by mapping the distribution of red supergiants detected by the 2MASS infrared survey. There are certainly other small galaxies in our local group that have not been detected yet. In general, rich clusters tend to contain 80 to 90% of E and S0 galaxies and a few spirals. In other words, galaxies that are crowded together tend to be E, elliptical, or spiral rather than S0 rather than spiral. Poor clusters contain a large percentage of spiral. Among the rare isolated galaxies that are not in clusters, over 80% are spirals. Somehow, the environment around the galaxy helps determine its type. Astronomers suspect that collisions between galaxies are an important process. Galaxies should collide very often. The average separation between galaxies is only about 20 times their diameter. Like two blindfolded elephants blundering about under a circus tent, galaxies should bump into each other once in a while. Stars, on the other hand, almost never collide. In a region of the galaxy near the Sun, the average separation between stars is about 10 times 7 times the diameter. Consequently, a collision between two stars inside a galaxy are less likely than a collision between two gnats flitting about on a football stadium. So notice 4 important points and 3 new terms. Interacting galaxies can distort each other with tides, producing tidal tails and shells of stars. They may even trigger formation of spiral arms. Large galaxies or even absorb smaller galaxies, a process called galactic cannibalism. Mr. Visagi, that is another American slang term for a jock. Secondly, interactions between galaxies can trigger rapid star formation. Thirdly, evidence left inside galaxies in the form of multiple nuclei and conflicting directions of star and gas motions reveals that they have suffered past interactions and mergers. Then lastly, the beautiful ring galaxies are understood to be bullseyes left behind by high-speed collisions. Evidence of galaxy mergers all around you. A Milky Way galaxy is a cannibal galaxy snacking on the nearby Magellantic clouds. Furthermore, our galaxy tides are pulling the Sagittarius dwarf galaxy apart, and the Canis Major dwarf galaxy has been almost completely digested as tides have pulled the stars away to form a great streamers wrapped around the Milky Way galaxy. Our galaxy has almost certainly dined on other small galaxies. The test of any scientific understanding is whether you can put all the evidence and theory together to tell the history of objects justified. Can you describe the origin and evolution of galaxies? Just a few decades ago, it would have been impossible, but evidence from space telescopes and new generation telescopes on Earth, combined with advances in computer modeling and theory, allows astronomers to outline the story of the galaxies. Before you begin, you should eliminate a few old ideas immediately. It is so easy to imagine that galaxies normally evolve from one type to another that you could call that a common misconception. But an elliptical galaxy cannot become a spiral galaxy or an irregular galaxy because ellipticals contain almost no gas and dust from which to make new stars. That means elliptical galaxies can't be galaxies. But you can also argue that spiral and irregular galaxies cannot evolve into elliptical galaxies because spiral and irregular galaxies contain old stars as well as young stars. The old stars tell you that a spiral and irregular galaxies can't be young. The galaxy classes tell you something important. But a single galaxy does not change from one class to another any more than a cat can change into a dog. Another old idea was that each galaxy formed from a single cloud of gas that contracted and formed stars, which astronomers refer to as a top-down hypothesis that we discussed last week. Abundant evidence now indicates that large galaxies, such as the Milky Way, do not form primarily by top-down contraction, but instead by a bottom-up accumulation of smaller clouds of gas and stars, the infall of gas and the absorption of small galaxies. Ellipticals especially appear to be the product of galaxy collisions and mergers. They are devoid of gas and dust because it was used up in the rapid star formation triggered by the interaction or blown away by the eruption of supernovae. In fact, astronomers see many starburst galaxies that are very luminous in the infrared because a recent collision has triggered a burst of star formation that is heating the dust, which radiates the energy in the infrared. Some of these galaxies are 100 times more luminous than our Milky Way galaxy, but so deeply shrouded in dust they are very dim at visible wavelengths. So in this image, we can see rapid star formation in image A. There's a starburst galaxy filled with clouds of young stars and supernovae. Image B, the dwarf irregular galaxy began a burst of star formation about 25 million years ago. Then in image C, at least some starbursts are triggered by interactions between galaxies. The inner part of M64, known as the Black Eye galaxy, are filled with dust produced by rapid star formation. Radio observations show that the inner part of the galaxy rotates backward compared to the outer part of the galaxy, a product of a merger, where the counter-rotating parts of the galaxy collide, star formation is stimulated. Many starburst galaxies show evidence of tidal tails and are probably the result of the merger of 3 or more galaxies that triggered firestorms of star formation and generated tremendous clouds of dust. An Antenna galaxy contains over 50 billion solar masses of hydrogen gas and will become a starburst galaxy as the ongoing merger continues to trigger rapid star formation. As these galaxies use up the last of their gas and dust making stars, they will probably become normal elliptical galaxies or merge to form a single elliptical. In contrast, spiral galaxies evidently have never suffered major collisions. Their thin disks are delicate and would be destroyed by the tidal forces generated during a collision with a massive galaxy. Also, they retain plenty of gas and dust and continue making stars. So they have never experienced a major starburst triggered by a merger. Of course, spiral galaxies can safely cannibalize smaller galaxies with no ill effects. The small galaxies do not generate strong enough tides to disturb the disk of a full-sized galaxy. You have seen plenty of evidence of cannibalism in our own galaxy, and some astronomers suspect that much of the halo consists of the remains of cannibalized galaxies. Eventually, our Milky Way galaxy has not collided with a galaxy of size comparable to itself. So far, however, other evidence indicates that our galaxy will merge with the approaching Andromeda galaxy in a few billion years, and the final result will probably be a large elliptical galaxy. Barred spiral galaxies may also be the products of tidal interactions. Mathematical models show that the bars are not stable and eventually dissipate. Tidal interactions with other galaxies may regenerate and sustain the bars. Well over half of all spiral galaxies have bars, suggesting that these tidal interactions are common. Other processes can alter galaxies. The S0 galaxy may have lost their gas and dust as they orbited through their respective clusters. A galaxy moving rapidly through the thin gas filling a cluster would encounter tremendous wind that could blow the galaxy's gas and dust away. In this way, a disk-shaped spiral galaxy could be reduced to an S0 galaxy. For example, X-ray observations show that a coma cluster contains thin, hot gas between the galaxies, and astronomers have located in similar clusters a galaxy in the act of plunging through such gas and being stripped of its gas and dust. Small galaxies may be produced in a number of ways. The dwarf ellipticals are too small to be produced by mergers, but it could be fragments of galaxies ripped free during interactions. Other small ellipticals may be the cause of larger galaxies that had their outer stars stripped away during encounters. In contrast, the irregular galaxies may be small fragments splashed from larger galaxies during collisions, but retaining enough gas and dust to continue forming stars. A good theory helps you understand how nature works, and astronomers are beginning to understand the exciting and complex story of the galaxies. It is already clear that galaxy evolution bears some resemblance to a pie-throwing contest. With the construction of the first large radio telescopes in the 1950s, astronomers discovered some galaxies dubbed radio galaxies. They were bright at radio wavelengths. Later, when telescopes went to orbit, these galaxies were found to be emitting energy at other wavelengths as well, and they became known as active galaxies. Modern observations show that the energy comes from the nuclei of the galaxies, which are now known as active galactic nuclei, or AGN. Only a few % of galaxies are active, but their activity makes them especially prominent. I have a few colleagues that specializes in AGNs, so that's also an interesting subject. So here we can see in the image below of visual wavelengths of a galaxy, but a radio galaxy that emits in other parts of the electromagnetic spectrum will look something like in the top image. So with which eyes do we observe the universe? So here we can see the visible light, infrared with Spitzer, the millimeter or submillimeter with ALMA, radio with the VLA, X-rays, radio and visible light, and X-rays with Chandra. Yes, Mr. Levuyo.
So are those all images of the same galaxy?
Yes, they are.
Of them, even the bottom ones, sir.
Yes.
And the one on the bottom left, so is that just inverted, like sort of?
This one right here.
Yes, sir.
So that is radio waves. So normal radio waves, that's in the megahertz. So let's say 80 to 120 megahertz. We will see radio waves emanating from these parts of the galaxy. So usually what happens is if we look at visible light, usually from the nucleus there are these jets that comes out, and these jets are only visible in radio waves.
Oh, that's cool. So thank you.
Pleasure. So, Seyfert galaxies. In 1943, Mount Wilson astronomer Carl Seyfert published a study of spiral galaxies. Observing at visual wavelengths, Seyfert found that some spiral galaxies have small, highly luminous nuclei with peculiar spectra. These galaxies are now known as Seyfert galaxies. About 2% of spiral galaxies appear to be Seyfert galaxies. So when you are near Mount Wilson in the US, you can visit this observatory. Seyfert galaxies are spiral galaxies with small, highly luminous nuclei. Some are interacting with nearby companions and appear distorted, with tidal tails and bridges. So here we can see NGC 7469 has a distorted companion at the lower left, so over here. Then here we can see NGC 410 is connected by a long tidal bridge and its companion. So you can see the tidal bridge. The spectrum of a galaxy is the blended spectra of billions of stars, and consequently weak spectral lines get washed out. Galaxy spectra contain only a few of the strongest absorption lines found in stellar spectra. In contrast, spectra of Seyfert galaxy nuclei contain broad emission lines. Emission lines are produced by a hot, low-density gas. So the gas and nuclei of a Seyfert galaxy must be highly excited. The width of the spectral line suggests large Doppler shifts produced by the high velocities in the nuclei. Gas approaching Earth produces blue-shifted spectral lines, and gas going away produces red-shifted lines. The combined light of gas approaching and receding therefore contains broad spectral lines showing that the velocities at the center of Seyfert galaxies are roughly 10,000 kilometers per second, about 30 times greater than velocities at the center of normal galaxies. So something violent is happening in the cores of Seyfert galaxies. The brilliant nuclei of Seyfert galaxies fluctuate rapidly, especially at X-ray wavelengths. The Seyfert nucleus can change its X-ray brightness by a significant amount in only minutes. As you learned when you studied neutron stars, an object cannot change its brightness noticeably in a time shorter than the time it takes light to cross diameter. If the Seyfert nucleus can change in a few minutes, then it cannot be more than a few light minutes in diameter, about the size of Earth's orbit. In spite of their small size, the cores of Seyfert galaxies produce tremendous amounts of energy. The brightest emit 100 times more energy than the entire Milky Way galaxy. Lots of energy is produced in very small volume with extremely high temperatures and velocities. What does that remind you of? Astronomers conclude that the centers of these galaxies contain supermassive black holes, orbited by hot accretion disks, which matter is flowing into the black hole. Early in this chapter, you learned about evidence that most galaxies contain supermassive black holes at the center. Nevertheless, most galaxies are not erupting. The shapes of Seyfert galaxies provide an important clue. About 25% of Seyfert galaxies have peculiar shapes suggesting that they have had tidal interactions with other galaxies. So in image A, we can see a Seyfert galaxy as part of a compact group of galaxies and is interacting with its smaller companion. In image B, we can see the tidal tails extending to the left and upper right are more easily visible in this enhanced image. So here we can see the effect on it. But here we can see the tidal tails and another tidal tail. There are also statistical evidence that Seyfert galaxies are more common in interacting pairs of galaxies than in isolated galaxies. These clues hint that Seyfert galaxies may have been triggered into activity by collisions or interactions with companions. You'll find more such evidence as you study other kinds of active galaxies. And now, the famous double lobe radio sources. Beginning in the 1950s, radio astronomers found that some sources of radio energy in the sky consisted of pairs of radio bright regions. Then optical telescopes studied the locations of these radio sources to reveal galaxies located between the two regions emitting radio energy. And the galaxies were dubbed double lobe radio galaxies. Unlike Seyfert galaxies, which emit intense radiation from their cores, these radio galaxies were producing energy from two external radio lobes. The shapes of radio lobes suggest that they are inflated by jets of excited gas emerging from the nucleus of the central galaxy. This has been called the double exhaust model. The presence of hot spots and synchrotron radiation shows that the jets are very powerful. You encountered synchrotron radiation previously, so we did in chapter 10 in the context of supernova remnants. Active galaxies that have jets and radio lobes are often deformed or interacting with other galaxies. The complex shapes of some jets and radio lobes can be explained by the motions of the active galactic nuclei. A good example of this is 3C31, the 31st source of the third Cambridge catalogue of radio sources with its twisting radio lobes. These jets are consistent with matter falling toward a central supermassive black hole and then somehow being ejected in two directions. In previous chapters, you have seen similar jets produced by accretion disks around protostars, neutron stars, and stellar mass black holes. Although the details are not entirely understood, the same process seems to be producing all of these jets. The evidence shows that the cores of many galaxies are occupied by supermassive black holes, with matter falling inward. As the matter falls towards the center, it releases tremendous gravitational energy and becomes intensely hot. The hot accretion disks can emit X-rays and eject jets in opposite directions. Now we're going to look at quasars. Through the 1950s, radio astronomers became familiar with celestial radio sources that were either huge clouds of gas or distant radio galaxies. So they were surprised in the early 1960s when some radio sources turned out to look like stars in visual wavelength photographs. First called stellar objects, they were soon referred to as quasars. Many more quasars have been found over the years, and most are radio silent. The radio astronomers stumbled over those emitting radio energy because they were easy to notice. Since their discovery, quasars has been a puzzle to astronomers. So here we can see quasars have star-like images, clearly different from the images of even very distant galaxies. Although quasars look like stars, their spectra are unlike spectra of stars or galaxies. The spikes on these images were produced by diffraction in the telescope. So here we can see a quasar, a galaxy, foreground star, and a different galaxy. The spectra of quasars were strange in that they contained a few unidentified emission lines superimposed on a continuous spectrum. In 1963, Martin Schmidt at Hale Observatories tried redshifting the hydrogen-Balmer lines to see if they could be made to agree with the lines in the spectrum of the quasar known as 3C273. At a redshift of 15.8%, three lines clicked into place. Other quasar spectra quickly yielded to this approach, revealing even larger redshifts. So here we can see this image shows the bright quasar at the center surrounded by faint fuzz. Note the jet protruding to the right. The original photographic plate holding a spectrum of 3C273 contains three hydrogen-Balmer lines: hydrogen delta, hydrogen gamma, and hydrogen beta. The spectrum is redshifted by 15.8%. The dashed line shows the unshifted position of the spectrum. So before I go on, are you guys familiar with these photographic plates? So photographic plates is a very, very old technology. But basically how it works is, you guys are familiar with the old Kodak film or Fujifilm that goes into film cameras. So when you take an image through the camera, the incoming light hits the negative film, and where the image is, the film will become lighter. That's the same principle with these photographic plates. It's the time before we had proper cameras. So you had a photographic plate, so a dark plate, and here's also a dark plate. And then when you shine an image on it through a telescope, where the light is hitting, it became lighter. And we saved that or kept that as an image of what we saw. So yes, here we can see a weird flare. So numerically, the redshift Z is the change of wavelength, so delta wavelength, divided by the unshifted wavelength. So this will give us the redshift. So according to Hubble law, these large redshifts imply very large distances. The first quasars studied were the brighter ones, but surveys have found many more. For example, the Sloan Digital Survey discovered 90,000 most of these quasars have very high redshifts and lie very far from Earth. Many quasar redshifts are greater than 1, and that may strike you as impossible. The Doppler formula implies that such objects must have velocities greater than the speed of light. But the redshifts of the galaxies and quasars are not produced by the Doppler effect. As you will discover in the next chapter, the redshifts are produced by the expansion of the universe, and astronomers must use the equations of general relativity to interpret them. Redshifts greater than 1 are not a problem and merely indicate great distance. Although the quasars are very far away, they are surprisingly bright. A typical galaxy at such a distance would be faint and extremely difficult to detect, but quasars show up on photographs at noticeable points of light. If you put the apparent brightness and huge distances of quasars into magnitude-distance relation, you will discover that quasars are ultra-luminous, having 10 to 1,000 times the luminosity of a large galaxy. Soon after quasars were discovered, astronomers detected fluctuations in brightness over time as short as a few hours. Those rapid fluctuations show that quasars are small objects, not more than a few light hours in diameter, smaller than our solar system. By the late 1960s, astronomers trying to understand quasars faced a problem. How could quasars be ultra-luminous but also very small? What could make 10 to 1,000 times more energy than a galaxy in a region as small as our solar system? Since that time, new large telescopes in space and on Earth's surface have revealed that quasars are often surrounded by hazy features whose spectra resemble those of normal galaxies. Evidently, quasars are located in galaxies. In addition, radio telescopes have revealed that some quasars are ejecting jets and inflating radio lobes. The evidence is now overwhelming that quasars are the active cause of very distant galaxies. In other words, quasars are the most extreme kind of active galactic nuclei. You now know that many galaxies contain supermassive black holes at the centers. Why do such objects produce eruptions and how do they form? So this is just a simulation. So here you can see the accretion disk, a supermassive black hole, a relativistic jet, a shockwave in this jet, the opaque inner regions of the galaxy. Matter falling inward toward a black hole spins very fast and becomes very hot. It spins because it must conserve angular momentum as it sinks inward, where it forms a flattened disk around a central black hole. Supermassive black holes have stronger gravity than stellar mass black holes and produced faster spins for the infalling matter at high temperatures. Even a supermassive black hole is surprisingly small. A 10 million solar mass black hole would be only 1/5 the diameter of Earth's orbit. So the matter can get close to the black hole and orbit very fast. The infalling matter heats up because it picks up speed, and as it collides with other matter, those high velocities become thermal energy. That is, matter falling inward converts gravitational energy into thermal energy and becomes hot. Theoretical calculations predict that a high temperature puffs up the inner part of the disk and makes it thick. Even closer to the black hole, an orbiting pole is unstable and must spiral into the black hole. So the innermost part of the disk is empty and the black hole is hidden deep inside an empty central well. Further out, the disk is thinner and cooler, but the outermost part of the disk, according to calculations, is fat, cool torus. So torus is a donut shape of dusty gas. Astronomers can't see black holes, but in some active galaxies, the Hubble Space Telescope can detect the outer parts of the central disks. Spectra reveal the speed of rotation, and Kepler's third law yields the mass of the central object. Some supermassive black holes have masses of a few million solar masses, like the one in the center of our Milky Way galaxy. But the most massive contain billions of solar masses. So here we can see the elliptical galaxy, NGC 4261, is ejecting jets and inflating radio lobes. High-resolution images show that the core contains a small bright nucleus orbiting by a spinning disk. This orbital velocity and size of the disk confirms that the central object is a supermassive black hole. So in this image, we can see the disk encloses 1.2 billion solar mass and is perpendicular to the axis of the jets, leading out to the radio lobes. The inner part of the accretion disk around a supermassive black hole can reach temperatures of millions of degrees and emit X-rays. In fact, cosmic ray detectors on Earth have observed ultra-high-energy particles that come from places in the sky occupied by active galactic nuclei. These powerful supermassive black holes and their hot accretion disks may be filling the universe with high-speed particles packing the wallop of major league fastballs. No one knows exactly how the supermassive black hole and its disk produces jets of gas and radiation. But magnetic fields are a factor. Because the disks is at least partially ionized, magnetic fields are trapped in the gas of the disk, drawn inward and wound up. Theory suggests that this creates powerful magnetic tubes extending along the axis of rotation, channeling hot gas outward in opposite directions. The jets seem to originate very close to the supermassive black hole, and are then focused and confined by the enclosing magnetic tubes. The mechanism that produces jets is understood in only a general way, but astronomers are now trying to work out the details. How can supermassive black holes explain all of the different kinds of active galaxies that are observed? When a field of research is young, scientists find many seemingly different phenomena, such as Seyfert galaxies, double-lobe radio galaxies, quasars, cosmic jets, and so on. As the research matures, scientists begin seeing similarities and eventually are able to unify the different phenomena as different aspects of a single process. This organization of evidence and theory into logical arguments that explain how nature works is the real goal of science. Astronomers studying active galaxies has developed a unified model of active galaxy cores that is well supported by evidence. A monster black hole is the centerpiece. According to the unified model, what you see when you view the core of an active galaxy depends on how the black hole's accretion disk is tipped with respect to your line of sight. You should note that the accretion disk may be tipped at a steep angle to the plane of its sight. So just because you see a galaxy face on doesn't mean you are looking at the accretion disk face on. So this is an artist's representation of this. In image A, artist's conception of AGN viewed edge-on with the view of the hot accretion disk and the central cavity around the supermassive black hole, blocked by the outer cool dusty torus. Then in image B, features visible in the spectrum of an AGN depend on the angle at which it is viewed. The unified model shown in cross-section suggests that matter flowing inward passes first through a large opaque torus, then into a thinner hot disk, and then finally into a small hot cavity around a black hole. Telescopes viewing such as a disk edge-on would see only narrow spectral lines from cooler gas. But a telescope looking into the central cavity would see broad spectral lines formed by hot gas. This diagram is not to scale. The central cavity may be only 0.01 parsecond radius, whereas the outer torus may be 1,000 parsecond radius. The spectrum you observe depends on the angle of the disk. If you view the accretion disk edge-on, you cannot see into the central area at all, and you see low temperatures and velocities. If a disk is tipped so you can see the hot inner gas, you see high temperatures and velocities. If the disk is nearly face-on, you would be looking directly into the central cavity, down the dragon's throat, and you would see extreme conditions. A few active galaxies have such extreme spectra. The unified model is far from complete. The actual structure of accretion disks is poorly understood, as is the process by which disks produce jets. The unified model does not explain all of the differences among active galaxies and quasars. Rather, it is a model that provides some clues to what is happening in active galactic nuclei. Now, triggering eruptions in these galaxies. Most galaxies contain supermassive black holes at their centers, but only a few % of galaxies have active nuclei. That must mean that most of the supermassive black holes are dormant. What could trigger a supermassive black hole to erupt? The answer is something that you studied back in chapter 4. Tides twist interacting galaxies and rip matter away into tidal tails. But mathematical models show that those same interactions can also throw matter inward. Even a small amount of matter falling into a black hole can produce an outburst. A sudden flood of matter flowing into the accretion disk around a supermassive black hole would trigger it into eruption. So here we can see a star possibly perturbed by an encounter with another star drifts toward a supermassive black hole. As the near side of the star tries to orbit faster than the far side, the star is torn apart by tidal forces. Most of the mass of the star is flung away from the black hole, but roughly 1% falls toward the black hole to form an accretion disk. This explains why active galaxies are often distorted. They have been twisted by tidal forces as they interacted or merged with other galaxies. Some active galaxies have nearby companions, and you can suspect that the companions are guilty of tidally distorting the other galaxy and triggering an eruption. Presumably, the AGN was triggered into activity by the same tidal interaction that pulled away the streamer. Galaxy IC 2497 provides a dramatic example of galaxy interactions and active nuclei. Near the galaxy lies a glowing green cloud of gas, named Hannies Voorwerp. The object is part of the streamer of gas, dust and stars pulled out of the galaxy by a recent interaction. When a beam of energy coming from the active nucleus of the galaxy shines on the streamer, the gas is excited to glow green in forbidden emission lines. Images of some quasars reveal that they are embedded in galaxies that are distorted and lie near other distorted galaxies. So in this image, we can see a beam of energy from active galaxy IC 2497 illuminates part of an infalling streamer of matter, exciting the gas to glow green. The glowing cloud was discovered by Dutch high school teacher Hanny van Arkel while using a personal computer with the Galaxy Zoo project, which recruits amateurs to classify the millions of galaxies found in deep surveys. The object's name, Hanny's voorwerp, means Hanny's object in Dutch. Now classified as a quasar, the active nucleus may have turned on as recently as 200,000 years ago. In this image, we can see two quasars are embedded in merging galaxies. Tidal forces have flung out tidal tails, a sure sign of galaxy mergers. Evidence shows that galaxies and supermassive black holes have evolved together. Astronomers can see this progression because at great distances, the look-back time is large and observations reveal the universe as it was long ago. The masses of supermassive black holes are related to the masses of the host galaxy, central bulges. In each case, the mass of the black hole is about 0.5% the mass of the surrounding central bulge, but there is no relation to the masses of the disks of the galaxies. This reveals that the formation of supermassive black holes were connected with the formation of the central bulge. They formed and evolved together. In the next chapter, you will see evidence that the universe began 13.8 billion years ago, and that it has been expanding ever since. Within a few 100 million years, the first clouds of gas began forming, stars, and falling together to form the great star clouds that became the central bulges of galaxies. The supermassive black holes formed at the same time. In fact, some evidence suggests that the black holes formed first and pulled matter inward to form central bulges. Matter flooding into these black holes would have triggered powerful outbursts. The formation of a central bulge was evidently a violent process. Eruptions of the growing central black hole could have pushed away infalling gas and limited the material available to form the stars of the central bulge. Also, infalling matter can trigger bursts of star formation, and resulting supernovae can blow gas out of a galaxy and also limit bulge growth. Some of the most distant quasars could have been caused by the formation of supermassive black holes, but these extremely distant objects are difficult to image with existing telescopes. Most of the quasars and other active galaxies that astronomers see with these telescopes have been triggered into eruption by the interaction, collision, and merging of galaxies, a process that throws matter into the central black hole. Collisions have been important in the evolution of galaxies and supermassive black holes. When the universe was young and had not expanded very much, galaxies were closer together and collided more often. Also, as small galaxies fell inward and formed halos and disks of larger galaxies, more matter would have been fed inward to supermassive black holes and triggered more eruptions. Observations showed that the first half of the history of the universe, each galaxy merged with other galaxies as often as 3 times every billion years. Most mergers were with smaller galaxies, but a few would have been with large galaxies and triggered eruptions visible from Earth today as quasars. Quasars are most common with redshifts over 2 and less common with redshifts above 3. The largest quasar redshifts are greater than 6, but such high redshift quasars are rare. Evidently, astronomers see few quasars at high redshifts because they are looking back to an age when the universe was so young it had not yet formed many galaxies. At redshifts between 2 and 3, galaxies are actively growing and colliding, and quasars were about 1,000 times more common than they are now. Nevertheless, even during the age of quasars, quasar eruptions must have been unusual. At any one time, only a small fraction of galaxies had quasars erupting in their cores. As smaller galaxies were gobbled up and the expansion of the universe carried the galaxies away from each other, galaxy formation became less active. Interactions between galaxies became rare, and quasars became even less common. Then where are all the dead quasars? There are no way to get rid of a supermassive black hole, so all of the galaxies that once had quasars must still have those black holes. Now dormant in their cores were all those dead quasars today. You know where to look, the cores of galaxies. Most large galaxies contain supermassive black holes at a center, but the black holes have consumed most of the nearby gas, dust, and stars and are now dormant. Our own Milky Way galaxy could have had a quasar at its core long ago, but now its central supermassive black hole is on a strict diet. A slow trickle of matter flowing into the black hole could explain the mild activity seen there. Occasional interactions between galaxies can throw matter inward and awaken a supermassive black hole into eruption, as a Seyfert galaxy or double-lobe radio galaxy. The active galaxies are not rare kind of a galaxy. They are normal galaxy passing through a stage that many galaxies experience. They are not really peculiar. They are an important part of the story of formation and evolution of galaxies. And that, ladies and gentlemen, is our lecture on galaxy formation and evolution.
So I have a request, sir.
Yes.
So until the end of lecture, sir, is it possible if we can do like like for example, so can we, instead of doing 2 hours a day, can we like at least do 1 hour and then like for 4 days? Cause so this is it's really hard to concentrate after the first hour.
I know, but unfortunately we need to use our 2 periods if we need to get through the last chapters of our coursework.
So even if you split up like the 2 hours into 1 hour intervals until like maybe until Thursday, we can do the lectures if it's okay with everybody else.
Unfortunately, then we won't be able to get through everything because looking at my semester planning, we are now on, let's see what we need to still go through. We have 1, 2, 3, 4, 5, 6, 7 sets of lecture slides we still need to go through.
Yeah, so what that person is saying, so what Lucas is saying.
We can take a 10-minute break between the periods.
Yo, cause this is cause like so you have a whole day of lectures and then this one is just
I can understand. So between the 2 lectures, we can take a short break.
Thank you, sir.
Awesome. I know this is a bit of information overload, but this is really cool work. So tomorrow, in tomorrow's lecture, we will be discussing an interesting topic, the black hole. And then from there on, we are going to discuss our own solar system, so the planets, how the planets are formed. And then we are going to end off this module with a fun chapter on extraterrestrial life. So that's why I thought. So this is probably the most. Galaxies is probably the most difficult part, but hopefully you are enjoying it.
Yes, hey, but it's just hard to pay attention. So after that, 8 hours, hey.
I understand. So so I will work in a few breaks in between.
Thank you, sir.
Okay, that's 100%, Mr. Visagie. Pleasure, guys. So, Mr. Visagie, you asked for re-explain a quasar. So, a quasar is an extremely luminous part of the center of a galaxy. Pleasure, guys. So the active galactic nuclei, or a quasar, is when we have a supermassive black hole and there is a accretion disk around it. And from the accretion disk, there are matter falling into the black hole. So all of a sudden, we have these jets being emitted with high energy particles such as X-rays, and that is a quasar. Yes, that is exactly related to Hawking radiation. Awesome, guys. So if you have no more questions, you are more than welcome to log off, and I will see you all tomorrow evening. Good luck with anything. If anything's happening tomorrow, then I will see you all tomorrow.